Hey everyone, so today we're going to be going over alkynes. That's going to include naming and kind of the reactions that you will need to know for test two. So the first part of the video is going to be going over the naming parts of it and just kind of going through that pretty quickly. We're not going to spend a ton of time on this. So with alkyne naming, alkynes are a functional group. So when I mean functional group, it's going to modify the parent chain and it's not going to be a branched group in front of the parent chain. It's always going to come at the end along with like your alkenes, alcohols, amines, and other functional groups like that. So a little review for a second. So alkanes end in A and E like hexane. Alkenes end in E and E, so like hexene. And then alkynes, and it's in the name, end in Y and E, so it'd be hexyne. These work the same way. If there's groups afterwards that have a vowel together, we would drop the E at the end of alkyne, but that's more of a specific case that we might get into for the naming. So we want to always do the same kind of method we have been doing for naming this entire time, and that's always following the longest parent chain. So what we're going to start with is going to highlight the longest parent chain, and then we're going to start numbering. So when you're looking at alkynes and alkenes, which we have one of each in here, priority-wise, they're the same unless there's a tie, and we'll get into that later. So we're just going to number 1, 2, 3, 4, 5. So we have two methyl groups. So we have 3, 4 dimethyl. And then our parent chain is a pentane, or 5 carbon chain. So it's going to be pent, 3-ene, which is where that double bond starts. And then it's going to be -1 -line. And that's the name for that one. So next up, we're going to once again highlight the longest parent chain. It's pretty simple here. It's just a straight chain right there. And then we're going to have to look to see which direction we need to number in. And so with alkynes being a functional group, you want to make sure that they have the lowest numbering when comparing it to like a branch group like a chlorine. So we're going to number that on the end closest to the triple bond. So 1, 2, 3, 4, 5, 6, 7. It's going to give us a 6 chloro. Then our parent chain is heptane, so 6 chloro hept. And then our alkyne starts on that 3 carbon right there. So it's going to be hept 3. All right, now moving on to this next one. So this is a way that Dr. Berg could potentially draw these. A little bit more confusing, just looking at it. We'll go through and label the carbons more clearly. So with this, I think I left the group off. So with this one, we have to count all the carbons. So when we do that, this is a carbon, this is a carbon, this is a carbon. This first part of the triple bond is a carbon. The end of it is a carbon. And then carbon there, carbon there, carbon there. So when you see it in like this straight chain format like this, when it's laid out, there's no angle to it. Just be careful when numbering your carbons. You don't want to miss any that are inside the triple bond. So now we're going to number. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Go number the other way. 1, 2, 3, 4, 5, 6, 7, 8. So our triple bond, both directions gives it a 4. So then it comes down to our priority groups. And in this case, we're going to go with our green numbering because bromo comes first alphabetically before chloro, even though they're both 2s. So it's going to be 2 bromo, 7 chloro. And then our parent chain is an oct, or 8 carbon, so oct. And then it's going to be 4 line, just like that. All right, now moving on to our next one. So this is where we start seeing some more of double bonds and triple bonds together. So once again, I'm just going to highlight main parent chain. Super simple right there. But then we have to look and see. So if we number this direction, we get one, two, three, four, five, six. And the other we get one, two, three, four, five, six. So when it comes to base priority, they are the same, alkenes and alkynes, but alkenes come first alphabetically. So when naming or choosing priority, and it gets down to a tie like this where it's a one and one, alkenes will come first. So for this one, our name is going to be, our parent chain is hex. It's going to be hex. And then one ene for our alkene on the very end right here. And then we're going to go down to our triple bond, which is going to be hex one ene dash five. And in this case, there's no E or Z on the double bond because both of those groups are hydrogens. We can show that really quickly. A little H there, H there. There's no difference. Impossible to choose which one. So now moving on to this last one, we have a couple of functional groups. We have an alkene, alkyne, and an alcohol group. So we're going to quickly just highlight the main parent chain right there. And then we're going to number. So one, two, three, four, five, six, seven, eight. So that gives us our lowest number for alcohol. If we went the other direction, it would have a five. Even though that gives the alkene a lower number, doesn't matter. The alcohol is the top priority group. And our functional group like kind of lists everything. So it's always going to want to have the lowest no matter what. So naming this one, our parent chain is oct. So it's going to be oct. And then that double bond is on the six. So it's going to be six ene. Triple bond is on the one. So one ine. Since we have an alcohol, we're going to drop that E right there. It's going to be four dash all. But then if we go and look at our double bonded carbon right there, or the double bond in the name, we can look at our groups and this has a hydrogen going down, hydrogen going up. And so it's going to be E because we have varying group sizes. So it's going to be E, oct, 16, 1I, 4 all. So do not forget to keep checking for your E and Z. And then as we get into it, other aspects for like naming molecules and everything. So that's very important to always look for if you see a double bond. So now getting a little bit into like the terminology for terminal alkynes and internal alkynes. So one thing to note, terminal alkynes have a pKa of 25, which is much less than internal alkynes, which have a pKa of 50. And so the difference between the two, so this is a terminal alkyne. And by terminal, I mean on the end. So even if, let's say we add another carbon, it's very much on the end. Um, it it will affect what kind of molecules are made from certain reactants, as you'll see in a little bit later when we get into the reaction part of this video. Um, but it's important to be able to recognize the difference between the two, as it will come up more later as we get more into chapter 7 and further on in the semester. So then if we're looking at an internal alkyne, so it's going to look something like this. So this just means it's like it's literally in the center. It's inside of the carbon chain. Um, and with this, like sometimes you can have multiple products with it being inside because it can bond to both. But on the terminal one, it's really only ever going to be, especially if it's like anti-Markovnikov, it's only going to be that end piece. But if it's like a Markovnikov reaction and you have an internal alkyne, you have to look and see if it can bond to both. If the products are a little bit different, but like have the same substitution pattern, then you'll have both products shown as your answer for the reactions. And that's something to note on the problem set we'll get to. So something to go back to just for a second. So when doing this, you're always looking, or when naming alkynes, you're looking for first pi bond. Wherever the first one starts, that's the one that's going to be the lowest or the priority one. So like with This one right to our left, the hex 1-ene 5-on. The reason that the ene is lower, so that's where the first pi bond is, and it has that first, obviously alphabetical order, it's higher. So that's why that one's chosen. But you always need to look and see like where the first pi bond actually starts. And that just means a double bond or a triple bond when referring to pi bonds. Okay, so now we can move on from naming and go on to some alkyne reactions, which are lots of fun. So to start off, we're just going to do addition of a halogen group pretty much, or HX as we like to call it. So it can be HCl, HBr, um, HI, things like that. So for this example, we're going to be adding HCl. And so with that, this reaction adds H and Cl, and it does it Markovnikov. A little refresher, Markovnikov just means adding to the more substituted carbon. So in this case, it's going to add right here, just like that. And if you want, you can leave hydrogens like that or draw them out kind of at an angle like that. So then after that, a lot of times you might see like two HCl as or two HBr as reactants. And so this is just showing the second step or what it would look like if you automatically did two. So it would be CH3 and then it would be dash C dash CH3 Cl Cl. So once again, it's Markovnikov, so it's going to always add to the more substituted carbon right there. Um, and that's pretty much what we're left with as our answer for that one. So now moving on to halogenation. In this one, we're going to be adding two BRs, so it's going to be that. And for this one, it's going to have some stereochem features, so it's going to be anti-addition. They're going to add on opposite directions. So with that, our reaction is going to look like this. We have our CH3 here, C. So one's going to be right here. Going to keep double bond like this. The other one's going to be going down. And we'll just put our H like that. So with this one, as long as you're showing that one is up and one is down, it doesn't matter like which side is up or which side is down, just that you actually show the difference. Because if you just write them both up, then it'll be kind of wrong on the problem set and on your exam and other things like that. So now if we look at the next one, this one is very similar. So I'll rewrite this for a little more clearly. 2Br2 or XS or excess Br2. So what that means, that just means that there is plenty of bromine floating around kind of in the reaction and everything. So you don't have to worry about like running out or anything. So it would automatically add four Br2s or four bromines in this case. Two Br2s gives us our four. And once again, this one is also anti-addition. But when we run, or when this reaction occurs, so it goes like this, C, Br, and then C, Br. That's what the first addition looks like. But then it's going to add anti the other way, like this. So it's not gonna, for this one, it's not gonna end up mattering in this particular problem like this. You're gonna have two up, two down like this. But just remember that there is anti-addition for this reaction in general. So now moving on to hydroboration. So this one is very similar to one of the reactions that we have for like alkenes. Um, it's like the B3H THF, and then we are adding like an alcohol group to um, the substituted carbon or the anti-mark position. Hydroboration oxidation works very similar to that in that it adds to the least substituted or the anti-mark position. So these reagents add a hydrogen, another hydrogen, and a double bonded oxygen. And then, like I said, this is anti-mark. So through the reaction mechanism, this reaction actually creates like an alcohol group added, but then it does some like mechanistically, the group is moved around and it is turned into, in this case, an aldehyde for hydroboration. So hydroboration creates aldehydes, and that's because it adds to that terminal alkyne position, giving us an aldehyde. And I'll show you that really quickly. So it's going to be CH3, CH2, C1O, H. So our two hydrogens were added to that center carbon right there, the CH2 carbon. That's where those went, and then the double bonded O went onto the C on the end. And this group right here is what we call an aldehyde. It's not incredibly important to know what an aldehyde is right now, but just knowing that this is what this reaction forms, it'll be important for synthesis later on. So it's important to know, very helpful and useful reaction as we continue in OChem. So now moving on to the next one, addition of H2O. This one is very similar to our H2O, H2SO4 reaction that we add onto alkenes, which gives us the alcohol into the Markovnikov position. So for this one, it's going to add the same thing as above, the two H's and the double bonded O. And like the one above, this one has a mechanism that helps create the double bonded O through like the removal of an H off the alcohol, flipping it around and stuff. Not super important to know how the mechanism works right now, or really in general for this one, just knowing that like the ultimate product of this reaction generates a ketone. So this adds to the Markovnikov position, or the more substituted position. And like I said, it creates ketones. So draw out the product right here. Just CH3, C, double bonded O right there, and then CH3. Our two hydrogens go into that N carbon right there, and we're left with a ketone. And ketones are this group right here. So when you have a double bonded oxygen in between two other carbon groups like that. And we're left with the ketone group right there. So now we're going to be moving on to some of the hydrogenation reactions. And so there's three ways to do this. You have H2 PDNC, H2 and then there's catalyst, and then Na or Li, along with NH3 and negative 78 degrees Celsius. So each of these kind of act in a special way for alkynes. I know we've seen H2PDNC with alkenes before, but in this case, when you have excess or abundant H2, it's going to act a little bit differently and fully reduce that triple bond, which I'll show you right now. So it's going to add four hydrogens, and there's no stereochem for this one. So when we're looking at our products, we have CH3 and our carbon here. It's going to become CH2, CH2, CH3. It completely reduces that triple bond by adding the four hydrogens into our center of the molecule. This is very helpful when trying to reduce double bonds, triple bonds, trying to get to a more like a fully saturated structure. It really just depends. This will be super helpful in synthesis when we get to that. You'll definitely see this on the exam, so definitely know like H2PDNC and how it can fully reduce a triple bond like that. So our next one is Lindlar's catalyst. So this one adds two hydrogens instead of the four from above. It's not as quite as strong of a reducing agent as H2PDNC. This one's a little bit weaker, but it does something special. So it has syn addition, which means cis. So when we add our hydrogens, it's going to be CH3, C, and then H there. Keep the double bond, H there, and then CH3 like that. Another way you can write it, or to be a little bit more clear, I'd recommend writing it like this to very clearly show that you have the two hydrogens going up and the other group's going down, or if you want to flip it, the methyl's going up and the hydrogen's going down. As long as they're in the same direction together, they add in the same direction. Now our next one, using these ions, sodium or lithium, this one actually adds the exact same thing, two hydrogens, but instead of adding syn, it has anti-addition or trans addition. So when we look at this product, CH3, C, put a double bond like that. So then we're going to have a hydrogen going up like this, methyl right here, and a hydrogen going down like that, and a methyl over here. So you have the one group going up, one group going down. That shows our anti-addition or trans-addition for this one. Knowing that about all three of these are very important for the exam, you will definitely have at least probably two of these because you need to make sure that you remember that like H2PNC fully reduces the triple bond. Lindlar's adds syn, the sodium or lithium. Make sure you know both. Adds trans because he will put that on there to try to trick you up and really test how much you know or remember from the class and what he's taught. So that's all for the reactions themselves. I'm just going to do a little bit more practice on the problem set and go over some of the answers for one of the groups that no one has. So for this first one, like I was showing earlier with HCl, we have CH3, C, gonna go to a double bond C, like that, and CH3 there. So we're gonna have our Br and our H. So in this case, it's gonna stop right there. We only have one unit. If we had two, then we could add another Br here, and then another H there. If we had a second HBr or excess HBr, that would occur. But in this case, the only thing that's actually going to happen is our product right there. So now our next one, we have one unit of Br2 and CH2Cl2. So in this case, we're going to be adding two bromines. If we had excess or two Br2s, then we would add four. But so for this one, it's going to be CH3 and 2R like this. One bromine there. And then each one gets one because it's anti-addition. So do not forget that, once again, anti-addition for this reaction, very important. Now moving on to the next one. So this is what I was talking about when I was mentioning internal versus terminal alkynes. So with this reaction, or these reagents, it generates an H, an H, and a double bonded O. So when looking at it, we have two places we can add that are both 2 prime, 2 prime. So we can add to both of those positions, equally favorable substitution pattern wise. So our first product is going to be CH3, CH2, C double bond O, CH2, CH3. That's our first product. Put it right there. And then our second product is just going to be moved over one, as you can see right there. So both of these form ketones. However, each one is slightly different, which is why we have two products. Now there are some reactions where just because of the triple bond internally does not mean that the actual products will be different. But in this case, these generate two distinct products, and we have to show both because there's no way to determine 100% which one is going to be there without doing like the physical reactions. So Dr. Bergson asked for both. And then the last one on this problem set, once again, is the exact same um, reagents. So it's going to be CH3, CH2, CH2, C, double bond, lone pairs there, and then CH3. So that's pretty much all for the reactions on here. Um, they're not too bad overall. Just definitely make sure you practice. Flashcards are key for this. Um, make sure you come into office hours. These are pretty much all the reactions we'll cover for test two, the alkene and the alkyne reactions we've gotten to right now. There might be a few more. Dr. Berg might sneak in right before the exam. But these are a big chunk of what you need to know. I guess just to wrap up, we'll do one more down here on the bottom. So if we used, instead of using these reagents, what if we used these reagents? So we'd have R2, BH, THF, NaOH, H2O, H2O2. So this reaction would generate an aldehyde rather than a ketone. So it'd be CH3, CH2, 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 C, and then H. So definitely knowing the difference between these two and which one like adds Markovnikov versus anti-Markovnikov is very important for the exam. Like I was saying, if you have any questions, please come by to office hours. Um, Otherwise, that is all that I pretty much have for today's video. Good luck studying, and I will see you later.